Hey, this is the worksheet 5 you picked up yesterday. Uh, Yesterday morning, I went through the first 2 pages, and so I'm going to start on page 3 or 7. Okay, given the function f of x, find the interval where the graph is concave down and increasing at the same time. So we're going to create 2 sine lines, a first derivative sine line and a second derivative sine line, and then we can line up 2 sine lines and see when the 2 behaviors are occurring at the same time. So find g prime. My critical points. Test each subinterval, -1 into my derivative. Negative times positive is negative, decreasing. Log 1n. Positive times positive is positive. 2n. Negative times positive is negative. And we know that these are just test numbers that we're not going to use in our interval statement. G double prime. Right, 0 into G double prime. I'll get positive. One into G double prime, get negative. So I'm looking for the interval where the graph is going to experience both concave down and increasing at the same time. So the only increasing that I see is here. And we see that this is concave up, this is concave down. We want to line it up here. So in this interval, my graph is going to experience both concave down and increasing. From 2/3 to 4/3. Okay, number 8, same idea. Find H prime, create your H prime sign line, find H double prime, find that sign line. And now we want to match up intervals of concave up with decreasing. Critical points from H prime is -5/3 and 1. Place them onto my H prime sign line. Test -2, test 0, test 2. Okay, find H double prime. That critical point. Here I'm testing 0 and 1. Sorry, -1 and 1. Looking for decreasing and concave up. So -1/3 to 1. Morning. We're on worksheet 5, page 3. Okay, any questions, 7 and 8? Okay, let's take a look at number 9. Number 9 says, where are the inflection points given our second derivative graph is showing? So if we're looking at a second derivative graph, we know the y-axis represents concavity. So we can label accordingly. Above is where the graph is experiencing concave up. Below is concave down. Anything on the x-axis are your potential points of inflections. Right. The Morgan's method table that can be helpful. We know that the point of inflection of the original will have to come from the x-intercepts of f double prime. But this comes with a little bit of condition here. If it's an x-intercept, it's only a candidate. What needs to happen in order for the x-intercept to be a point of inflection? There has to be a what? Yeah, has to be a change in signs. Okay, so keep that in mind. Not every x-intercept is going to be a point of inflection on the f double prime sign line, f double prime graph. Got to change sides. So here's my f double prime sign line. X-intercepts are C, E, and I. To the left of my first critical point, where's my f double prime graph located? Above. So above is going to correlate with concave up. Don't look at the shape, look at the location. Between C and E, clearly below the x-axis, that's going to correlate to concave down.
Wait, why'd you put I on the line if it's not changing stuff?
You're right. It's not going to be a point of inflection. I just put it here to indicate that it's a candidate, but we're going to see there's no change in sign, so we can eliminate it. But if you already see it, you don't have to go through this whole thing.
Anything that touches the line should be put on the.
Yeah, that's typically how that's typically how we do our second derivative sign line as well, right? Anything that hits 0, we put on the line, and then we look to see if there's a change in sign. But if you can already see it without having to go through this, then that's fine as well. Between E and I, above the x-axis, concave up. The right of I also concave up. So this goes to show that I is a critical point, but it is not a point of inflection because there's no change in signs. There's only going to be 2 points of inflections at C and E. And our justification is because f double prime changes signs. And as future reference, if there's ever a free response question on the AP exam, the graders are instructed to not look at sign lines. So they're going to be looking at what you conclude from the sign lines, but the graders are instructed not to look at the sign lines. That's really just for your benefit or for the student's benefit. Okay. Any questions? Okay, let's do a derivative graph. Next page. Okay, so you're going to create a derivative f prime sign line, f double prime sign line, then you're going to graph f of x, you're going to graph f double prime. I left out a lot of things like, where's the graph increasing, decreasing, concave up, concave down. I figured that if you have the sign lines in front of you, those are going to be pretty obvious. I think the practice that we want is, can we create the sign lines? Can we create our function? Can we create our f double prime? Right. So this is our f prime graph. It's labeled accordingly. F prime graph is indicating our slope values. So above is where slope is positive, below is where the original graph is going to be experiencing a negative slope. So go ahead and find those x-intercepts first. Okay. Between -6 and -4, our graph is clearly below the x-axis. That's going to correspond with a negative slope. Between -4 and 2, positive slope. Between 2 and 4, above the x-axis, so still positive slope. Between 4 and 5, negative slope, below the x-axis. Next up, if we're trying to find a point of inflection off of f double prime, the point of inflection on the original function is going to show up as the max and mins of the f prime graph. So if we can find the peaks and valleys of f prime, those will be locations where my original graph is going to be experiencing points of inflections. Right? So -2, +2, sorry, it's +2, -2, +2, and 3. Now we can look at the movement of the graph. Okay, here, these are negative slopes, all of a sudden turning into positive slopes. So a negative slope turning into a positive slope, it's going to end up looking like this, right? On the original graph, right? Negative slope, slope 0, positive slope. Negative slope, 0, positive slope. So whenever my f prime graph is increasing in slope, my original graph is going to end up looking like concave up. Okay. Negative slope on my f prime graph is going to translate to concave down. Positive slope on my f prime graph will translate to concave up. Negative slope on my f prime graph, concave down. Don't look at the curvature. This is not the original function. So we don't want to say, oh, this is concave down, this is concave up.
So on the right side of the point of inflection, it's always going to be concave up, and the left side of the point of inflection is going to be concave down.
Are you talking about left and right?
Yeah, so like to the right of that, it's always going to be.
Well, not here though. To the right, to the left of this, it ends up being concave down.
Okay, so unless it's like attached.
Yeah, I would say look at the slope, right? Positive slope means concave up, negative slope means concave down. Or if you want to visualize what's happening, right? Imagine a negative slope of -3, then -2, then -1, then 0, then 1, then 2, then 3. If you were to visualize if you were to plot all those slope behaviors on the original graph, this is what your graph will end up looking like, right? Concave up. Yeah.
Why are the max and mins points of inflection? Is it just because it's like halfway in between?
The reason why is because these are the maximum and the minimum steepness on the graph. So if you're on a roller coaster ride, the maximum and minimum steepness of your graph could be like slope of -3 or slope of +4. And that's going to end up looking like the peaks and valleys of the f-prime graph. Okay, are we good with the sign lines?
I have a question for the like F prime like that.
Yeah.
Like, so since they gave us the F
Prime graph, yeah. You're looking at this column here. So the x-intercept of an f prime graph is going to look like the potential max and mins on the original function graph. So yeah.
for the like concav like the F of double
Yeah.
that thing like we would
Yeah, you would we're looking for points of inflections, right? We want to find points of inflections off the original graph. So points of inflections off the original graph will look like max and mins off of the f prime graph.
okay. Yeah, I was thank you.
Wait, can you explain that again?
Yeah, so the points of inflections off of the original graph will look like the max and mins off of the f prime graph.
Okay, so like if I was given the original graph,
Yeah.
I would go and I would just use that one row.
If you're looking at the original graph, then your points of inflection would be what you would where you would expect it to be. It's where your curvature changes, like these points, right? But typically what's going to happen is I'll be giving you an F prime graph and you're trying to interpret where to find the max and max mins and points of inflections of the original graph. And
So
the max and mins of the original graph will be located as x-intercepts of the F prime, and the points of inflections of your original graph will show up as max and mins on the F prime graph.
So if it's asking to go back, you would just use the x-intercepts, then you would say those are the maximums, and then you would use the minimums and max to find the point of inflection of the original graph.
Right. So this is what's going to happen, right? I'm going to give you F prime. So you just have to know how to get to this behavior from this graph. Yeah, there'll be one extended question like that. Yeah.
Oh, so like for the like F double prime graph,
Yeah.
the point of inflection of the F graph equals the max F of prime, and then the x-intercept of F double prime.
Yeah. So we saw on the last problem, that's what happened, right? The last problem, because we're looking at the F double prime graph, the points of inflection will show up as the x-intercepts.
Okay. And then what are the maxes and mins on the F double prime graph?
That's one level down that we're not to worry about. Yeah.
Wait, so for this one, the maximums are gonna be the
max and mins on the F double prime graph will be showing something a level down that we don't have to worry about. Okay. So now the next challenge is, can we sketch our f of x graph just based off of these behaviors? So my suggestion is find a way to cover up your f prime graph, because if you look at your f prime graph and graphing your f is going to throw you off. I think the best way to do this is force yourself to only look at your sign lines, because this is all you need to build out the picture of your graph, right? These arrows are supposed to help us make our way through the graph. So we're expecting, how do we expect our original graph to look? A relative what?
relative.
Minimum, okay? And it's going to rise. And then whenever there's a tick mark, we know there's going to be a leveling off, right? So the graph is going to level off at some point at x equals 2. It's going to continue rising, hit a what? Maximum somewhere at 4, and it's going to fall after that. So our graph needs to follow the directions of these arrows. Okay. These are our anchor points. So we're going to plot those points first. So -6, 3, and 5, 8. Okay, so I'm going to lightly trace because I'm not going to commit to this graph yet, but I do want to at least map out the path of my graph. So my graph is going to start falling, and then somewhere at -4, I'm going to hit a relative min. Let me say somewhere here. You could go lower if you want. It's just that I'm looking ahead to see what my graph needs to be. My graph needs to have to live between a y value of 1 and 10. So I'm just kind of looking for that possibility that the graph may be hitting the lowest y value there. And then we know our graph is going to rise after that. And then somewhere at 2, I want my graph to level off. And then at 4, it's going to hit a relative max. And after that, it's going to fall. So And my relative max is probably going to be my highest point because it's going to have to be all the way up at 10. So this could be the path of my graph. So I'm just following what the arrows are telling me, decreasing, increasing, flattening out at 2, increasing, relative max at 4, decreasing to my endpoint. After that, my points of inflection. So wherever the graph lands at -2, I'm going to highlight that point. Wherever the graph lands at 2, I'll highlight that point. At 3, I'll highlight that point. And now I'm just going to retrace the graph with the proper curvature that I'm hoping that I want the graph to show. Concave up first, followed by concave down, followed by concave up, and the rest of it is concave down.
Wait, so what was the point of drawing red points?
So that I can retrace and give it more distinguished curvature. Because the dotted line is just, I'm just connecting the dots. I didn't really think about what the curvature was going to be. I didn't know the curvature information until I got to it.
So for the test, should we like, is this like a good question to study for?
Yeah. Well, and then when you leave, you can pick up. I have 2 more practice problems that we can do in class. So yeah, you have a problem that looks pretty much like this. It's going to ask you more information about, you know, increase, decrease, relative max, relative min, but you guys know how to do that. So I left that part out. Okay, so that's f of x graph. And also at the end, we want to make sure that our graph is exhibiting this range behavior. So range behavior shows my lowest y value needs to be at 1. My highest y value needs to be at 10. So you can just indicate that you have those points identified. Okay, here's my f of x. Let's look at f double prime. So to do your f double prime graph, all you need is your sine line here. Okay. So
Wait, we only look at the.
Yeah, just look at your f double prime sine line. So as a reminder of what we're looking at, our y-axis represents concavity. So above is concave up. Below the x-axis is concave down. On the x-axis are your potential points of inflections. Okay, so start off with your x-intercepts, right? Your x-intercepts on your f double prime graph will be potential points of inflections off the original graph. So -2, +2, 3. That's it. All you're doing is you're just threading your graph between these points. You just have to know where your graph's going to live. Don't look at the shape. Some students try to build in the shape and it ends up looking more complicated than the graphs before it. This should look the simplest out of the 3. We'll have the least number of curves. So where do we want to start?
-6 and -6.
Yeah. So what does that mean?
So it needs to be over the.
Above, right? Yeah. So it needs to come down like this. So it's going to come down. We know these anchor points will kind of help guide us where our graph is going to have to go. From -2 to 2, where do we want our graph to live? Below. So it's going to go down, come back up. From 2 to 3, above, go up, come back down. To the right of 3.
So even though, like, when you look on the line, it says technically it's supposed to be concave down, like, it's just based off of it, it's above or below.
Right, yeah. Because we don't want to look at the shape, right? The shape is meant to describe the original function.
Okay.
The shape is not it's not meant for the second derivative. All right, let's do a optimization problem. And then, oh, and also to double check, right? All of our graphs should look different, right? I see some students, they look at their f prime while they're graphing their f of x, and it ends up looking the same. So they should look very different from each other. That's a good sign as well. And this should be the simplest looking. This is the one that has one additional change in direction, and this should be the most complicated looking.
For the, for graphing the f of x graph, if our like points to inflection are like, are just not as like exact.
No, yeah, so it doesn't, your y values may be different than mine, which is okay. Your y value may be higher or lower than mine, but it should be pretty close to the graph that I have,
Yeah.
since we have our restriction with our range.
Yeah.
Yeah, that's fine. Okay, let's try this optimization one here, page 5. Square base, so I can make my base x and x. Height, I'll use different variable, h. Volume is x squared times h. We have a restriction with volume. Volume is 30 square meters. If I solve for h is 30 over x squared. This is an open top, so we have 5 sides that where there's going to be material that we have to account for. So you got the base, which is x squared. You have one of the vertical sides, which is xh. If there's a vertical side of xh, there's also an opposing xh on the other side. And then the front face is also xh, so there must be a back side that's also xh. So we have 5 areas of rectangles all accounted for. Area of the base, area of each of the 4 sides. So it's 5 total.
Wait, how'd you get x squared?
I got that's the base.
Uh,
Right. The bottom is x and x. So once we have our surface area, we can factor in the cost. So the base is the more expensive material, $15 per square meters.
wait, if it wasn't an open top, there would be 2x.
So it'll be x squared plus x squared. But open top means there's nothing covering one side of the box. So the 7 has to be multiplied into the sides. So this is 4xh. 4xh times 7 is 28xh. So here's my cost equation, 15x squared plus 28xh. I do want to find the derivative, but that h needs to be resolved. So I'm going to use my volume equation to help me make that substitution. Once I get that substitution in, now I'm just trying to get it cleaned up, getting ready for power rule, find the derivative, find the critical point.
Why is it 27x8? Why is it 28xh?
Because my surface area is 4xh.
Okay.
and I have to multiply the size by $7.
Oh, so you multiply each one by 7? Just
Yes,
each side.
right. Or you can add the size up first and then multiply the 7. It's up to you. Either way, we gotta involve that $7 for each of the sides.
Wait, I'm confused.
Mhm.
Oh, wait, never mind.
How would you like find the like not the cube root?
Cube root, if you do math,
Uh-huh.
oh, wait, I mean, different calculator. Oh, yeah, math 4. Math 4 will get you cube root.
Oh, okay, thank you. This is just the three.
There we go, yeah.
So for this, do you just like find your two equations and then plug in, normally you're gonna plug in H and then you take the derivative of that, which of when you plug in H.
No, because once you solve for X, you're done with all the calculus. You're just plugging in and finding information.
Okay.
Yeah. So if it's asking for dimensions, then you need the X, and H. If it's asking for surface area, then just plug into your surface area equation. If it's asking for cost, just plug into your cost equation.
How do I know when to take the derivative of?
You found the derivative from C to C prime. That's the only time you do derivative.
Okay. And then you just find the zeros of that.
That's right. Yeah, that's the only time you use calculus. Just that one step. Everything else, you're just either setting up or cleaning up. Oh, because my base and my width are the same values, right? Length, width are the same and the height is different. Yeah, it'll be just like that.
So won't be one of the ones where like it folds up.
No, it'll be this.
Non-offensive. And can we always round to like 3 decimals?
Yeah, that's usually AP exam as well. If they don't specify, it's 3 decimal places. Tomorrow I'll do a half session, 7:10 to 7:45.
Is it, that's gonna look like a lot like,
Yes,
or like these 3 pages that we just did.
yes, but I think if you go to page 29, this is really what it is. You got to have prime derivative graph, you got optimization, you got a curve sketch problem, which we did yesterday, like page 1 and page 2. We got build everything from scratch, and we have 3 problems, problem 5.53, like EBT mean value result. So yeah, it's a mixture of what we've been doing the past few days.
First derivative test and second derivative test, and just sort of increase the D.
Wait, first derivative test and test for concavity is just, it's just increase, decrease, and concave up, concave down. Second derivative test is we gotta find max and mins using f double prime,
Oh, yeah.
right? Yeah,
Yeah.
yeah. Okay, see you guys. Class.
Yeah, mine don't either.
It's a-
You don't